And here we are, starting with, of course, question number 1, which gives us two first-order differential equations, one of which, part B, is actually an initial value problem, and asks us to solve it. So we'll talk about the difference between solving an initial value problem versus solving a differential equation on its own when we start with part B. But the main thing I want to focus on right at the start here is how we determine which method we should apply to, first of all, part A, and then to part B, to actually solve these differential equations. Because we've got a whole bunch of methods. Even if we just think about our first-order differential equation solution methods, there are still several ways that we can go about that. And anytime you've got a lot of choice in accomplishing fundamentally the same thing, i.e. solving a differential equation, sometimes that can be a little confusing and a little intimidating to just try to navigate the question of, well, of all those methods we were introduced to, what's the right one here? And so basically, I approach this through a series of questions. So let's look at part A to begin with. We've got t times dy dt minus y equals cosine t times y cubed. So the first thing I usually look at is this a separable differential equation? So in other words, can I rewrite this so that I can take all the expressions involving y and bring that to one side of the equal sign, and all the expressions involving t and bring that to the other side of the equal sign? If I can do that, then this becomes a pretty straightforward problem. I just integrate both sides. Hopefully the integration wouldn't be too messy in that case. And then if it's a linear equation, I know that I'll be able to solve explicitly for y in terms of t. And if it's nonlinear, maybe I can do that, or maybe I'll just have to leave this in some implicit form. We'd have to see at that point. Well, is this separable? Can I take all the expressions involving y and all the expressions involving t and pull them apart? It doesn't look like it. Because in order to do that, I would probably have to take that minus y and bring it over to the right-hand side of the equation. So I'd have cosine t times y cubed plus y. And then how do I get the cosine t and the y cubed apart? There's not a whole lot I can do. If I factor out a y from the right-hand side, then I'd have y outside of cosine t y squared plus 1. So that doesn't do it. If I factor out a y cubed, I've got y cubed times cosine t plus 1 over y squared, which doesn't really do it. The cosine t plus y squared then is kind of a unit. And I don't know what other approach we might use to try to rewrite this equation to get the y's and the t's separated. Every now and then you'll encounter a separable equation where there's a really clever approach to separating the variables. A particularly clever factoring or application of a trigonometric identity or something like that. But nothing seems to be coming to mind here. So it's probably not a separable equation. Okay, that's okay. Sometimes figuring out that a certain method can't be applied is just as valuable as identifying one that can. So now that we know that this doesn't seem to be a separable equation, the next question I'd ask is this a linear differential equation? And so remember, equations are nonlinear if we've got products of y and or its derivatives, if y or its derivatives are stuck inside other functions, anything like that. Basically anything so that our differential equation isn't just a linear combination of functions of t multiplied by y or by derivatives of y and functions of t and constants on their own. Here, we've got a y cubed, so we've got y stuck inside a power of 3. And that tells us this is a non-linear differential equation. So in particular, because we've already figured out that we're not going to be able to use the method of separation of variables, what knowing that this is a non-linear differential equation tells us now is that this also can't be solved by the method of integrating factors. Because the method of integrating factors specifically required a first-order linear differential equation, and we don't have that here. Okay, so we need one of our nonlinear techniques that isn't separation of variables. And at this point, depending on how your particular instructor approached the course, you'll see a bit of variation here because there are lots of methods for solving particular first-order nonlinear equations. And we could have spent the entire semester just talking about all these different methods. Certainly, I tried to keep things reasonably simple and accessible by paring that down to just a few very common methods. So one method that we talked about was the method of homogeneous equations, which is a method that takes a nonlinear equation that isn't separable and makes it separable. Could we use that here? Well, in order to do that, we have to solve for dy dt. So we'd write this as dy dt equals cosine t times y cubed plus y all over t. And we take that function on the right-hand side, and we would ask the question, if I replace t with a constant k times t, and y by the same constant k times y, do all my k's cancel? So in other words, is f of t comma y equal to f of k times t comma k times y? So then we'd have cosine of kt times ky all cubed plus k times y all over k times t. And yeah, we get some cancellation of k's there, but nothing is going to get at that k that's inside the cosine in particular. So no, all those k's don't cancel. Therefore, this is not a homogeneous equation. The other major class that we talked about was a method that would take a nonlinear equation and make it linear. That's the Bernoulli equations. So is this a Bernoulli equation? Well, what makes it think a Bernoulli equation is if it's basically in the right form for a linear equation, but what would be the non-homogeneous function of t, what I call in class g of t, the thing that we normally write on the right-hand side of the equation, if that's instead multiplied by some power of y to some power n, that's what would make it a Bernoulli equation, and it looks like that's exactly what we've got here. If that y cubed wasn't on the right-hand side, this would be a lovely little linear first-order equation. So it looks like we're going to want to use the Bernoulli equation method to solve this ODE. Let's see how it would work. So this is a Bernoulli equation. With the n, the power of this extraneous nonlinear factor of y, n is 3 in this case. So the first thing we do then is we take the differential equation and we divide through by y to the n. We get it off that right-hand side, we move it over to the left-hand side. So right now, as given, I've got t times dy dt minus y equals cosine t y cubed. So if I divide through by y cubed, I'm going to have t times y to the negative 3 dy dt minus y over y cubed would be y to the negative 2 equals cosine t. And now I have to make a substitution, because my goal here is to take this from a nonlinear equation and turn it into a linear equation. And the substitution, I'm going to call the new variable v, is we let v be y to the power of 1 minus n, this would be the formula. But really, all that I think about is, well, once I've rewritten my Bernoulli equation in the form that I just did, I look at what used to be my y term, that I've now divided by y to the n, to get y to the negative 2, that power of y is what I'm going to let v be equal to. So I let v be equal to y to the power of negative 2, so that dv dt is going to be negative 2 times y to the negative 3 dy dt. And really the useful thing here is because I've already got, in my first term, I've got t times y to the negative 3 times dy dt. That would tell me that negative 1/2 times dv dt is y to the negative 3 dy dt. So that's going to let me get rid of anything in my differential equation that involves y. So now I'm going to have t times negative 1/2 dv dt minus v equals cosine of t. Or in other words, negative 1/2 t dv dt minus v equals cosine t. that is now a linear differential equation. My new unknown function v only appears in two places. It appears in dv dt, which is only multiplied by functions of t, and is not itself stuck inside any kind of a function. And it appears as v itself, which is only multiplied by the constant function -1, and again is not stuck inside any sort of function. That's linear. That's what we wanted. So because it's now linear, we can kind of start the problem all over again. We can ask, is this separable? And no, it's not, and typically it won't be. But if nothing else, with linear differential equations, the method of integrating factors is always an option. We just have to make sure that we take our linear ODE and put it into the right form. Namely, we need the derivative of the unknown function, so in this case dv dt, to have as its coefficient just the constant 1, whereas right now we've got -1/2 t. So in other words, I've got to divide through by -1/2 t. Okay, well that's not so bad. So then that'll give me dv dt plus 2/t times v equals 2 times cosine t all over t. And so now that tells me that the two functions of t that are active here, the coefficient of v, which I call p of t, that's 2/t, and the non-homogeneous function g of t, that's going to be 2 cosine t all over t. P of t is the particularly useful quantity right now, because that's what explicitly comes up in the method of integrating factors. So our integrating factor mu is equal to e to the integral of p of t, which is going to be e to the integral of 2/t, which is e to the power of 2 times the natural log of t. Now, depending on how your particular instructor taught this material, you might include the absolute values in the integral there. You might be looking for an indication in the differential equation that t is greater than 0, something like that. When I teach the course, I indicate that those can be natural assumptions unless there's specific information otherwise, which is why I would leave the absolute values out here. But I guess in this case it really doesn't matter anyways, because when we bring the 2 in, we want to bring that inside the logarithm now as an exponent, and we're going to get t squared either way. So whether we included the absolute values or not, once we square it, that becomes irrelevant. So I can write that as e to the power of the natural log of t squared, and now I can cancel out the exponential and logarithmic functions because, of course, they're inverses. So that tells me that my integrating factor is just t squared. Now I'm going to take t squared, and I'm going to multiply through the current version of my differential equation by that expression. So now we rewrite the ODE as t squared times dv dt plus t squared times 2/t would be 2t times v. And likewise on the right-hand side, I'll have t squared times 2 cosine t over t is going to be 2t cosine t. When we apply the method of integrating factors, the differential equation can always then be rewritten in the exact same form. The left-hand side in particular will always reduce to the derivative with respect to t of the integrating factor, t squared, times the unknown function, which in this case is v. So that's going to be the derivative of t squared times v on the left-hand side, and you can double check that. Use the product rule and make sure it works. Equal to the right-hand side, 2t times cosine t. which tells us now that t squared times v is the integral of 2t cosine t. And I'll move over to the next page. And that's not an elementary integral, but it's not a terribly hard integral, I hope you'll agree. It's just it's integration by parts that we'll use here. So I use kind of non-standard notation for integration by parts. Most texts and most instructors will write the integration by parts formula as an expression involving u and v, where u is the thing that you differentiate and v is the thing that you integrate. I don't like that because, well, we commonly use u for u substitution. It's right there in the name. There are many other letters of the alphabet, and we often use substitution and integration by parts together, and then you just have to change your notation anyways. So I use w to represent the thing that you differentiate anyways, but of course it doesn't change anything about the method. So in this case, I'm going to let 2t be the thing that I differentiate, or I could have factored the 2 outside the integral altogether. Either way is fine. So that dw is 2 times dt, and then that would leave the thing that I'm integrating, my dv, is cosine t dt, so that v is sine t. So that tells me that t squared times v is equal to w times v, so 2t sine t, minus the integral of v dw, so minus the integral of 2 sine of t, and of course now that is an elementary integral, so the right-hand side there becomes 2t sine of t, plus 2 cosine of t, plus a constant of integration c, which then lets us solve for v. So dividing through by t squared then, v is 2 times t to the negative 1 times sine of t, plus 2 times t to the negative 2 cosine t, plus c times t to the negative 2. And I've written this in terms of negative powers just because it makes the writing a little bit easier, keeps it all in one nice small line. If you prefer to use denominators here, divide by t and t squared, of course that is absolutely fine. And so finally then, we need to switch back to our original variables. So v we define to be equal to y to the negative 2, so it's y to the negative 2. That would be equal to 2 times t to the negative 1 sine t, plus 2 times t to the negative 2 cosine t, plus c times t to the negative 2. Whether you do any more work beyond this line, it would partly depend on how your particular instructor has suggested that you write these things. So for instance, we could solve for y kind of. We could take the reciprocal of both sides and have y squared equals 1 over all the expression I've got there on the right. And so then y would be plus or minus the square root of that reciprocal. That's not a terribly nice way to write it. We could solve for c. We could multiply through by t squared, for instance, and collect everything except the constant of integration c. We could bring all that over to the left-hand side. These would both be pretty typical ways to do it, or frankly, you could leave it where it is. I personally would be quite fine with this expression as we've written it here, but of course, always go by the pattern established in class. That's your safest bet. But there we go. We have taken this nonlinear first-order equation, this Bernoulli equation. We have applied the appropriate substitution, which lets us do the method of integrating factors because the substitution makes the equation linear, and we wind up being able to find at least an implicit solution of the equation. So there's part A done. I'm going to continue part B in the next video in this playlist. I will see you there.